everyone. Today we'll be going to chapter 2 chapter summary for capacitors and dielectrics. For chapter 2 you have capacitance and capacitors in series and parallel, and you have charging discharging of the capacitors and capacitors and dielectrics. So we go to the first subtopic. So we have the main equation of capacitance is C is equal to Q over V. C is the capacitance with the unit of farad, and Q is the charge with the unit of coulomb, and V is the voltage with the unit of volt. So that is the basic equation of capacitance. Capacitance is the ability to store charge, ability of certain capacitor to store charge. And for series and parallel, we have to know that for the charge, it is equal in all the capacitors in the circuit. And for the parallel arrangement, you have to add up all the values of the charge flowing in each capacitor. Then you total up the numbers, then we'll get your charge total. And for potential difference, for series, you have to add up the values, and for parallel, the potential equal for all of the capacitors. This is the important equation that is for capacitance, for series, and also for parallel. And this is the equation for U. U is the energy stored, okay, in the capacitor. Okay, so since this is the basic equation, half CV squared, C is equal to Q over V. You can also have the equation, you can define or you can expand the equation. So it can be half QV and half Q squared over C. For charging discharging, okay, so basically this is the the graph of charging is Q against time. So for charging, of course, the charge is going up. Okay, it starts from 0 to maximum. And this is the equation of charge for charging. And this one is the equation for current for charging. So current is decreasing. And this is the graph of discharging. Okay, we remove the charge from the capacitor. So it starts with maximum charge here until it will reach almost 0. This is the equation for charge for discharging. And if you could differentiate or distinguish these two equations, they are having the same equation. When the charge flowing, current is always decreasing, but your discharging, for your discharging process, your current is flowing in opposite direction. So the equation can also be negative I naught over RC. For both current against time graph, for both charging and discharging, you can have this type of graph. It is exponential decreasing. For the last subtopic, for chapter 2, we have capacitors and dielectrics. Okay, so basically you have originally you have a capacitor between the symbol is the capacitor, so you have two plates, and originally it is air-filled capacitor. In between these two plates, it is filled with air. But if you insert dielectric, let's say we put on a dielectric materials, okay, what happened is it's going to be, okay, increasing your capacitance. So capacitance without dielectric is symbolized as C naught normally, and capacitance with dielectric is, we symbolize it as C. So why it is increasing? Okay, we have a long discussion for that reason. It is because when you insert dielectric, so the total electric field inside in between the two plates is decreasing, and as E is equal to V over D, so when E decrease, V also decrease, and C is equal to Q over V, so when V decrease, C is increasing. So that's the reason why when we insert dielectric material, the value of capacitance is increasing. So this is the equation, basic equation for air-filled capacitor without dielectric. So we have the area is only for one plate, okay, the surface area of the plate. D is the distance between the two plates, okay, we have D here. And you also have the term epsilon r. So epsilon r is known, it is known as the dielectric constant. So dielectric constant here is to be applied when you want to calculate the equation of capacitance, okay, capacitance with dielectric field. Okay, so now your equation becomes C is equal to, you have the factor of dielectric constant C naught, or you can express the equation of capacitance with dielectric field as ER E naught A over D. Then you also have a few cases. Okay, sometimes question asks you, when the battery removed from the circuit or disconnected, what happens to the charge, voltage, and capacitance? When you remove the battery, hopefully you can still recall that battery supply voltage. So when you remove the battery, meaning that the voltage will decreasing, but the charge is still there, so it is constant. So based on the equation, C is equal to Q over V, as the V decreasing, so capacitance will increase. So that's for the case of battery disconnected. But if you have the case of battery still connected, once again battery supplies voltage, so when it is still connected, the voltage constant, and C will increase, and also Q is increased. The ability to store charge is increasing when the battery is still connected. Okay, the ability to store charge is the capacitance. So that's all for chapter 2, the summary for chapter 2. Okay, thank you very much.